Welcome to this video on Chapter 10, Chemical Bonding. We will explore how atoms interact, form compounds, and develop stable structures. In this video, we will cover bonding models, representing valence electrons with Lewis structures, and the formation of ionic and covalent compounds. Bonding theories are crucial in science. For example, researchers used these models in 1989 to study HIV protease, a protein essential for the HIV virus to replicate. By understanding the structure of HIV protease, scientists developed protease inhibitors that disable the virus, helping patients manage HIV and live healthier lives. Bonding theories allow us to predict which atoms will form stable compounds. They explain, for instance, why common salt is sodium chloride rather than sodium chloride. The Lewis theory is a fundamental approach named after G.N. Lewis. It uses dots to represent valence electrons and remains a simple, powerful tool for predicting molecular structures. To represent valence electrons, we place dots around an element symbol. For main group elements, the number of dots equals the group number. For example, oxygen has an electron configuration of 1s 22s22p4, giving it 6 valence electrons. Its Lewis structure displays these A6 dots. When drawing these structures, fill in the dots one by one before pairing them. This convention is standard practice in chemistry. Here you can see the Lewis structures for period 2 elements. Atoms with 8 valence electrons, known as an octet, are particularly stable. Writing the structure for phosphorus is straightforward. As a group 5a element, it has 5 valence electrons, represented by 5 dots surrounding the p symbol. Helium is an exception to the octet rule. It has only 2 electrons, forming a stable duet, which represents a complete, stable configuration for this element. In Lewis theory, a chemical bond occurs when electrons are either shared or transferred to reach stability. This defines the difference between ionic and covalent bonds. The octet rule guides us here. Atoms generally bond to achieve an outer shell of 8 electrons. Helium, lithium, and hydrogen are the key exceptions, aiming for a duet. Finally, when metals and nonmetals bond, electrons are transferred. The metal becomes a cation, the nonmetal an anion, and their electrostatic attraction forms an ionic compound. In ionic compounds, electrons are transferred. For instance, when potassium and chlorine bond, the potassium atom transfers its valence electron to the chlorine atom. This electron transfer allows chlorine to achieve a stable octet, while potassium, having lost its valence electron, also achieves an octet in its inner shell. The resulting potassium cation and chloride anion are attracted by electrostatic forces to form the compound KCl. Anions are typically written within brackets with their charge indicated. When writing the Lewis structure for magnesium oxide, magnesium transfers its 2 valence electrons to oxygen, resulting in a stable Mg2 plus cation and O2 anion. Lewis theory helps predict correct chemical formulas. For sodium and sulfur, 2 sodium atoms are needed to provide electrons to 1 sulfur atom, resulting in the formula sodium sulfide. In contrast, covalent bonds occur when nonmetals bond with other nonmetals. Here, electrons are shared between atoms rather than being transferred. In a water molecule, hydrogen and oxygen share electrons. This allows each hydrogen atom to reach a stable duet and the oxygen atom to attain a stable octet. Shared electrons appearing between atoms count toward the octets or duets of both bonded atoms, ensuring stability for each. Shared electrons are known as bonding pairs and are often represented by dashes. Electrons exclusive to a single atom are called lone pairs. Lewis theory explains why halogens exist as diatomic molecules. By pairing together, 2 chlorine atoms can share electrons to each reach an octet. Similarly, hydrogen exists as H2. When 2 hydrogen atoms share their valence electrons, they each achieve a stable duet configuration. Atoms can sometimes share more than 1 electron pair to satisfy the octet rule. For oxygen, creating a double bond helps both atoms reach stability. By forming a double bond, each oxygen atom now effectively has an octet, with the shared bonding pairs counting toward both atoms. Triple bonds can also form. For the nitrogen molecule N2, converting 2 lone pairs into bonding pairs allows each nitrogen atom to achieve a stable octet. In summary, double and triple bonds are stronger and shorter than single bonds. These bonds are essential for understanding the properties of many stable molecules found in nature. To write Lewis structures for covalent compounds, first determine the skeletal structure. This shows the relative positions of atoms, though it excludes electrons. Remember that hydrogen atoms are always terminal because they only require a duet. Additionally, molecules are often symmetrical, so similar atoms usually occupy terminal positions. Next, calculate the total number of valence electrons. For main group elements, this matches the group number. For polyatomic ions, adjust for the charge. Subtract for positive, add for negative. Now distribute these electrons. Start by placing a bonding pair between every atom, then assign the remaining electrons to terminal atoms first, and finally the central atom to complete octets. If any atoms still lack an octet, you can create double or triple bonds by moving lone pairs from terminal atoms into the bonding region with the central atom. Let's look at carbon dioxide, CO2. Its skeletal structure is OCO. With 4 valence electrons from carbon and 6 from each of the 2 oxygens, we have 16 total electrons. We place the bonding pairs, then distribute the remaining electrons as lone pairs. Finally, we convert 2 lone pairs into double bonds, so that every atom satisfies the octet rule. For polyatomic ions, the process is similar, but don't forget to account for the ion's charge in your electron count. Always enclose the final structure in brackets with the charge indicated. For the cyanide ion, Cn, we start with the skeletal structure and sum the valence electrons. 4 for carbon, 5 for nitrogen, plus 1 for the negative charge, totaling 10. After placing bonding pairs and lone pairs, we move 2 pairs to form a triple bond between the carbon and nitrogen, ensuring both atoms reach an octet. While the octet rule is reliable, there are exceptions. Some molecules like NO have an odd number of electrons, and boron compounds often form with only 6 electrons around the central atom. Other molecules exhibit quote, expanded octets, where the central atom has more than 8 electrons, such as sulfur hexafluoride. Despite these exceptions, Lewis theory remains highly effective. Sometimes, a molecule can be represented by multiple valid Lewis structures. For sulfur dioxide, we can draw 2 equivalent structures by changing which oxygen atom forms the double bond. These represent resonance, where the true structure of the molecule is an average of these possibilities, rather than a single fixed arrangement of electrons. By understanding resonance and these bonding models, we gain deeper insight into the complex and stable structures that define the chemical world around us.